Hello, everyone. Thank you for joining me today on my presentation. My name is Abdulghani. I'm a Master of Applied Science graduate from the University of Windsor. I'll be presenting part of my thesis research on differential variable speed limits to improve performance and safety of car-truck mixed traffic. Okay. So, as we all know, speed is one of the most important factors affecting the crash risk on highways. Neglecting the speed on roads and highways will lead to a higher number of crashes. For this reason, the speed limits have been posted to regulate the speed of vehicles. The speed limits are usually applied as a uniform speed limit, same speed limits for all types of vehicles, like cars and trucks. USL does not consider the different traffic and weather condition, and also the uniform speed limit does not consider the difference in driver behavior and vehicle performance between cars and trucks. So what's the problem with that? Heavy trucks can impose negative impact on the traffic performance and safety because of their large size and heavy weight, such as a limited and restricted maneuverability, longer stopping distance, and stronger impact in the case of collision. So, numerous studies have been conducted to develop effective speed control strategies to improve road safety and traffic operation. Such strategies are the differential speed limit and variable speed limit. The differential speed limit assigns different speed limits for cars and trucks, usually lower speed limit for trucks than cars. And the variable speed limit assigns different speed limit depending on the weather and traffic condition. Usually, speed limits are displayed in this strategy on different types of dynamic messages called DMS. Those dynamic messages help driver identify the upcoming events and reduce their speed in advance. Studies have shown that DSL and VSL can improve traffic and performance. So, although differential speed limit can consider the difference in car and truck movement, and variable speed limit can consider the variation in traffic condition, there has been a lack of studies on the integration of both differential speed limit and variable speed limit. So, different speed limits for cars and trucks in different traffic condition, or what we will call from now on differential variable speed limit, DVSL, can potentially better control speeds of car-truck mixed traffic flow in congested condition. So there is a need to develop such strategy and test the impact of differential variable speed limit on mobility. The dynamic message sign, here we have one example that we would display on the roads or highways. So to investigate the effects of different speed limit strategies, such as differential variable speed limit, traffic on a 2.9 kilometer segment of 3-lane westbound Gardner Expressway in Toronto was simulated using the VISIM traffic simulation. On this segment, there is 6 loop detector stations separated by about 500 meters, where those loop detector can extract data such as average speed and occupancy. The current speed limit on this highway is uniform speed limit of 90 kilometers per hour. The truck percentage on the expressway in the afternoon peak period is about 5 to 15%. So there is the Jameson Avenue, the entrance ramp. The entrance ramp from the Jameson Avenue is closed from 3 to 6 and reopens at 6 p.m. Due to this reopening, sudden congestion occurs upstream of the entrance ramp. So this daily routine schedule of ramp closure and ramp reopening causes congestion to occur in the merge area after the ramp reopens. And thus there is a flow breakdown, as we can see here in the picture, where after 6 p.m. there's a congestion upstream of the open ramp. So VISIM was used to simulate the traffic on the studied freeway segment for about 3-hour period from 4:30 p.m. to 7:30 p.m. before and after the ramp opens. 4 speed limit strategies have been tested here: the uniform speed limit, the differential speed limit, and differential variable speed limit. The uniform speed limit is 90 for car and trucks, the same speed that is being used now. Differential speed limit is 90 kilometers per hour and 80 kilometers per hour, so 10 kilometers difference. And the differential variable speed limit, where this algorithm that we will use changes the speed limits in real time based on the congestion level and track percentage detecting using the loop detectors. So the proposed differential variable speed limit strategy in this study determines car and truck speed limits based on the following factors: track percentage, the level of congestion, whether it is uncongested condition, mild congestion, and severe congestion, and the speed upstream of the congested area, which we will use right now, the station 100, as we see from this graph. So the differential variable speed limit algorithm considers the difference between car and truck speeds and determines different speed limits for cars and trucks when track percentage is high. The level of congestion was observed as station 100, which is closest to the on-ramp on Jameson Avenue, where the congestion is first detected when the on-ramp opens. So here, as we can see on the first level of DVSL algorithm, the speed at station 100 is compared with the threshold speed or the critical speed of 60 kilometers per hour to classify the traffic condition to either mild and uncongested or severe congestion. When the speed at station 100 is higher than 60 kilometers per hour at level 2, track percentage at station 100 was compared with the threshold, which is here 10%, to classify the track percentage into either low track percentage or high track percentage. On the third level, we have in this DVSL algorithm, the occupancy at station 100 was compared with the critical occupancy to classify traffic condition into either, as we can see here, uncongested condition and mild congestion. So in the uncongested condition, in both high track percentage or low track percentage, depending on the track percentage, we can say here that in the uncongested condition, we use uniform speed limit, and or in the higher track percentage, we use differential speed limit. So different speed for cars and trucks because of the higher track percentage. In the mild congestion, where the speed limit at the road section upstream of the station 100 was set to the average speed in the section, when the occupancy is higher, when the occupancy is higher than critical occupancy, we have the mild congestion. Sorry. We use variable speed limit, same speed for cars and trucks in low track percentage, and variable speed limit different for car and truck in higher traffic percentage. So we go back to the speed at station 100. When the speed at station 100 is lower than 60, we would have severe congestion. In that case, we would use spatial coordination. What is spatial coordination? So spatial coordination in which speed limits are gradually reduced in multiple locations before reaching the congested area at station 100 upstream and closest to the ramp. The spatial coordination of speed limits ensure more gradual changes in speed over space and increase driver compliance with the speed limits. For instance, assume that the congestion occurs at station 100 and that the speed suddenly dropped from 90 kilometers per hour to 60 kilometers per hour. To allow gradual deceleration at the road sections upstream of the station 100, speed limit can be first reduced from 60 to 50, then from 40 to 30, on the different station from 70 to 100. Okay, results. By comparing the traffic performance and car delay, truck delay, total delay, it was found that all delays were constantly lowest for DVSL compared to the other strategies, USL and DSL. This is because differential variable speed limit assigns the speed limit closer to the observed speeds than the other strategies and can reduce the variation speed in particularly congested conditions. We also compared the crash risk, comparison of average probability of collision. Crash risk was calculated for the 3 strategies and 3 vehicle pair types: car following car following truck, and truck following car. Collision risk was significantly higher for truck following car conflicts than car following car and car following truck. Differential variable speed limit had the lowest crash potential index, which means the lowest collision risk for all type of vehicles. This is because differential variable speed limit allowed smoother and gradual speed change for cars and trucks in the congested condition. In conclusion, differential variable speed limit strategies can potentially improve both traffic performance and safety of traffic flow. Also, the differential variable speed limit decreases the risk of rear-end collision for all types of conflicts, particularly the risk of more severe collision, which is the truck following car. Some future studies, we would evaluate the differential variable speed limit in different traffic and road geometric conditions. We could also evaluate the weather-based differential variable speed limit and maybe test it using a driving simulator.
Thank you very much. Hi everyone, my name is Zahra. I am from Iowa State University, and thank you everyone for joining this webinar. Today I'm going to present our work titled Impacts of Phase Assignment on the Operational Performance of Traffic Signals. In this study, we compare more flexible timing as exemplified by the 8-phase control scheme against simplified 4-phase control schemes that either couple together opposing left and through movements, or each approach, also known as split phasing. The 3 separate experiments are conducted to ascertain the difference between these 3 types of phase assignments on the signal operation. And to our knowledge, this hasn't been studied in any published previous literature other than a few older case studies comparing 8-phase versus stage-based control. So before going to explain the experiments, I would like to briefly explain a phase-based control. Actually, a phase-based control scheme is shown in this figure, and as the name dual ring would suggest, 2 rings are employed, and each ring may serve one phase at a time, and the ring may choose to serve any phase is a member of the ring subject to some rules. The most important rule is that both rings must serve a phase within the same concurrency group at the same time, which means that they must also cross the barrier at the same time. For example, it is acceptable for phase 2 to be served at the same time as either phase 5 or 6, but never 7 or 8. The flexibility of phase-based control arises from the fact that other than barrier crossing transitions, the 2 rings are able to switch phases independently. That is, phases 1 and 5 don't need to end at the same time. One could end earlier or be omitted if there is no traffic. Actually, the flexibility of phase-based control can be seen in this intersection, which occurs in a right-hand traffic country. Its major street is oriented in the east-west direction with separate lanes and signal heads for left turns, which operate in a protected permitted configuration. And the minor street is oriented in the north-south direction and doesn't feature separate left turn lanes or signal heads. In this example, the actual intersection doesn't have a need for left turns from the minor street, so phases 3 and 7 can be left out, and the timing of each phase is separately handled by the two rings. And the decision to end phase 1 early would be based on the observation that volume 1 has no more demand. Thus, ring 1 makes terminates phase 1 without consulting ring 2, which continues to serve phase 5, likely based on an observation that volume 5 continues to have demand. Later, when crossing a barrier, both rings must transition at the same time. For example, here from 2 and 6 to 4 and 8. And in the second cycle, there is no need to serve phase 5 at all, so it is skipped. And the second ring goes directly from phase 8 to 6 independently of ring 1. So in this slide and the next slide, I'm going to explain the three-phase sequencing that we use to see how they impact the operational performance of the traffic signals. The first one is the 8-phase control. Actually, the 8-phase control, or 8P control, is common in the US, and as we see here, two rings run concurrently. Another thing about 8-phase control is that transition across barrier must be coordinated across all rings, while transition within barriers may occur freely and is dynamic under actuated control. Um, the second and third phase sequencing that we used are four-phase concurrent pattern and four-phase approach-based. Actually, four-phase control is rarely used in the field in the US, but the assumption of this type of operation is frequently made in papers on advanced signal control methods, possibly to avoid difficulties of modeling 8-phase control. Actually, in a four-phase concurrent pattern, which is shown here, the opposing left turns and through right turn movement share phases, and we name it 4P. And in four-phase approach-based pattern, which is shown here, each approach or leg of the intersection operates concurrently, with the left and through right movements operating simultaneously, and we name it 4PA. So so we call four-phase concurrent pattern 4P and four-phase approach-based pattern as 4PA. The first experiment that we conducted is this experiment, which is a single fully actuated intersection. For this experiment, we created a simulation model of a single intersection in vSTEAM with two volume scenarios, as it is shown here. And the signal timing information for 8-phase and 4-phase controls are also shown here. Actually, the purpose of this test is to assess two different impact comparison. The first one is the impact of phase sequence, and the second one is the impact of lane by lane versus a series detection, which is well known to have a strong impact on actuated operation. Here is we can see lane by lane detection and approach based detection. Actually, in lane by lane detection, each lane gaps out independently and it detects gaps within lanes, and approach based detection can only detect gaps when all lanes are empty. So the results of these, of the first experiments that we conducted show that lane by lane performs better than series control with substantial reduction in total delay. Also, the results show that the use of 4P and 4PA results in greater impact of lane by lane versus when the same comparison is done with 8P. Actually, this illustrates that use of simplified phase sequences can magnify the effect of a change like use of lane by lane. For the second and the third experiment, we analyzed the impacts of phase sequence on corridor operations. So to analyze the impacts of phase sequence on corridor operations, for the first experiment, we looked at impacts of phase sequence for a series of corridors with random intersection spacing. And for each randomly generated network, we optimized the cycle length, splits, and order of phases for each type of sequence. And we modeled the results using Robertson's platoon dispersion model similar to transit for this experiment. And the results which are obtained for 370 random networks show that the performance index, which includes delay and stops, is lowest under 8 phase, followed by 4P, with 4PA having the highest performance index. For the last experiment, to analyze the impacts of phase sequence on corridor operations, we created a VC model using a section of Jordan Creek Parkway in West Des Moines, Iowa, with 3 signalized intersections. And as we see here, this is our corridor with 3 signalized intersections and their volumes. Actually, the purpose of this test is to assess 3 different impact comparisons. The first one is the impact of phase sequence. The second is to compare impact of choice of optimization software. In this case, we compared Synchro and Vistro. And the third one is to compare the impact of choice of cycle lengths. Actually, for 8 phase and 4P, 140-second cycle length could be used, while 4PA required a 190 second cycle length. And as in the single intersection study, the goal is to see whether these comparisons have similar impact or not. So actually, the results of these experiments show that the change in delay due to phase sequence is similar in magnitude to the choice of cycle length and often more impactful than the choice of optimization software. As we see here, there is relatively minor difference resulting from choice of software. Also, the results show that 8P and 4P are similar in terms of performance, with 8P tending to be better, although not always. Additionally, the results show that 4PA has consistently bad performance that is far worse than 4P and 8P, even under the same cycle length. In this slide, I'm going to summarize all observations from 3 experiments that we conducted. For a single intersection, the phase sequence had an impact roughly half as great in terms of delay differences than the use of lane by lane versus series detection. For a corridor, the phase sequence had about as much impact as the choice of cycle lengths, more impact than the choice of simulation software. Finally, the 4PA option performed particularly poorly compared to the other phase sequences. So in this slide, which is our last slide, I'd like to talk about the suggestions from this study. First of all, results suggest that use of 8P would be the best option in future research of advanced traffic control methods. Moreover, the choice of phase sequence doesn't have a negligible effect. It is not something that should be taken care of later in favor of pursuing a particular control concept in the short term. It needs to be solved upfront. And finally, in some cases, the impact of an operational change might be magnified with the use of less flexible phase sequences. So field results in real-world implementation may not live up to simulated performance if simplified phases sequences were used. Okay, thank you very much for your attention. Please let me know if you have any question.
Good afternoon, everyone. My name is Peter Yu, and I'm an undergraduate student at the University of Washington. And first of all, I'd really like to thank PTV Group for hosting such an excellent student talks edition. It's really awesome, as well as everyone for attending today's session. So today I'll be presenting on enhancing the operational efficiency of signalized diamond interchanges with the new design that I created called the Displaced DDI, Displaced Diverging Diamond Interchange. So, and again, I would really like to thank PTV Group again for hosting such an excellent student talks edition, as well as providing me with the necessary software, PTV Visum. Without their support, it would have been very difficult to do this. So thanks again. As well as PACTRANS, Pacific Northwest Transportation Consortium, Region 10, for supporting my work as well. So first of all, in recent years, we've been considering a lot of alternative intersections and interchanges. It's because, first of all, these interchange ramp terminals, they are essentially the backbone of the highway network. Whenever you want to get on or off the freeway to do a major road trip, you do have to go through these interchanges. So it's very crucial that these interchange ramp terminals be optimized for efficiency and safety. Also, we have increasing traffic volumes, and with COVID, we're going to expect a lot more single vehicle trips. So continuously increasing traffic volumes. We also have aging and deteriorating transportation infrastructure, and a lot of this infrastructure just can't really support this increase in traffic volumes. And also we have financial and environmental constraints and just not much right of way. So these are the main reasons why we're considering alternative intersections and interchanges. So this is the most common type of interchange design on freeways, the conventional diamond interchange. Of course, it has two signalized intersections, one for each ramp terminal that they're coordinated. It's the most common type of interchange, and it works pretty well under low to moderate traffic volumes. However, as traffic volumes do become heavy, the level of service just does tend to decrease, and the left turning traffic at the ramp terminals tends to become the greatest impediment to operational efficiency. And so beyond that, in the past, what many agencies would implement would be the SPUI, or single point urban interchange, where everything is consolidated into a single signalized intersection right in the middle of the interchange. Of course, this has the advantage of creating just one signalized intersection, which should be safer and more efficient. However, the two main disadvantages of the SPUI is that it requires a really large grid structure, as you can see here. In many cases, when they're converting an existing conventional diamond interchange into a SPUI, they would have to tear down the old bridge and completely rebuild the new bridge, which would be very expensive and time-consuming. Plus, it doesn't accommodate pedestrians well. Many cases, there is no crosswalk for pedestrians to cross from one side of the arterial to the next. So many times pedestrians will have to use an adjacent traffic signal to cross, which would take a very long walk in this case. So to address all these deficiencies, the final design that transportation agencies are just really using a lot today is the the DDI, or Diverging Diamond Interchange. Of course, this has the main advantage. Its main feature is that traffic briefly travels to the other side of the road before moving over to the proper side of the road. Again, it has two signalized ramp terminal intersections. And really the main advantage here is that it's really inexpensive to build. you can basically use the existing grid structure of the conventional diamond interchange and basically just reconstruct the ramp terminal intersections, which only takes probably around 8 or 9 months compared to a SPUI, which would take maybe 2 or 3 years. It also has the advantage of efficiently handling left turning movements. It can handle a lot of left turning traffic without any problem, but its main disadvantage is that it's not the best option to choose. It's less efficient when there are high through volumes, as you wouldn't be able to provide enough green time or good progression for each direction of the arterial. So to anticipate all of these problems and try to solve them in terms of the DDI, I first saw that in Missouri, they considered this displaced net interchange, and they actually built it. Interchange of I-35 and Missouri Highway 152 in Liberty, Missouri. Of course, they considered both the SPUI and DDI, but all were eliminated in the end due to the various problems I listed in the previous slides. And compared to a traditional diamond interchange, this serves approximately 1,500 more vehicles in the peak hour and 30% less travel time and 45% less delay. So when I looked at this, I decided to make some modifications, and after making some creative modifications, I came up with the what I call the displaced DDI, or displaced diverging diamond interchange. It's pretty similar to the displaced net interchange, except that left turning traffic has its own have their own exclusive lanes, and this would make traffic flow easier and safer. Also, I didn't show it in the picture here, but this wouldn't be one huge bridge structure. It would be two separate bridge structures. This is the bridge structure of the existing conventional diamond interchange if you're going to convert a CDI into a displaced DDI. And these 4 lanes make up a second new bridge structure that you would build if you're going to convert it. It has many separate traffic signal nodes or many small intersections to ensure two-phase operation. So here are the basic vehicle paths of the displaced DDI. The through traffic and right turning traffic basically move the same way as they would in a conventional diamond interchange. The main difference comes in the left turns. So if you're going to turn left from the arterial to get onto the freeway, these are the 2 paths that you would take depending on which direction you're going to go. If you want to turn left from the freeway onto the arterial, on the other hand, these are the 2 paths that you would take to get onto the arterial from the freeway. And here are the pedestrian paths that pedestrians would have to take to get through this displaced DDI. There are crossings and provisions provided for pedestrians who want to cross from one side of the arterial to the next, to the other side. So, and here's the basic traffic signal design of the displaced DDI. You can see here that there's a total of 5 nodes or 5 distinct intersections. Each node has 2 critical phases, so this definitely provides an advantage over other designs which may have to use 3 or 4 critical phases. You can see here that these nodes 1, 2, 3, and 5 are half signaled, meaning that they only control one direction of the arterial as opposed to 2. Node 4 right here, it's a full signal, which means it controls both directions of the arterial. The main advantage of doing this or having the half signals is that once we define the timing of node 4, you can, and because nodes 1 and 2 operate independently than that of nodes 3 and 5, you can basically provide perfect two-way progression for each direction of the arterial. Once you define the timing for node 4, you can set up the timings for 1 and 2 and 3 and 5 such that there's perfect progression for each direction of the arterial. So this should definitely be good for progression and through traffic. And so to analyze the operational performance of the displaced DDI, first, I determined the yellow, change, and red clearance intervals of all traffic signals using ITE's new guidelines, which was published just last year in March 2020. I also used PTV Visceral, did some work there to help analyze the traffic signal timing and help optimize the traffic signal timing and modeling before using VISM. And finally, I implemented the optimized signal timing plans and PTV vism for each scenario. And my MOEs, or measures of effectiveness, were network travel time and the total number of stops. And so here's the operational comparison that I did. I compared the displaced DDI with the conventional diamond, the SPUI, and the DDI. And of course, here are my key geometric features that I used for each interchange and in each scenario. And this is just a detailed list of the traffic volumes that I used to simulate very congested traffic volumes and congested diamond interchanges. I used a volume to capacity ratio of 1.15 in the CDI using critical lane volume calculations and analysis, 5% heavy vehicles. Also considered 3 traffic volume conditions: balanced, heavy ram, and 60/40 arterial. All are pretty typical of many service interchanges that you would find in the field. Also 3 net turning traffic volume conditions to provide some diverse traffic volume, some diverse traffic volumes to simulate it under a wide variety of traffic volume conditions. And of course, I did a total of 600 simulation runs, since there were a total of 15 traffic scenarios, and I used 10 simulation seeds for each simulation scenario. Also, here are my desired speeds, and also I ran each simulation for 4,500 seconds, 900-second warm-up, and 3,600-second data collection period. And also, of course, right turns of red were permitted, except in the DDI, since it's recommended by the DDI informational guide not to do so. And so here's just a quick simulation video of how the displaced DDI would operate under the balanced and moderate turning traffic volume scenario. You can see here that each direction of the arterial does have basically almost perfect progression. You can see here that each car basically gets a green light as soon as they get to the next signal. They get a rear end collision, but no real damage is done here. So this is basically how the displaced DDI would typically operate. It's basically one huge traffic signal controller, and this is fixed time control to optimize the progression and bandwidths and signal timing. Yeah, this is basically how the displaced DDI would operate. And so here are my operational results for travel time after I compiled all the results. I used the mean total network travel time for each scenario in vehicle hours. So the results showed that the displaced DDI provided the least amount of travel time overall out of all 4 interchange designs. And in most cases, it was statistically significant. Only a few cases, as you can see here, that are listed in bold, were not statistically significant. So definitely a lot of travel time to be saved with the displaced DDI. Also, the number of stops. The displaced DDI did consistently result in the least total number of stops in comparison to the other 3 interchange designs. You can see here that still only a few scenarios and designs were not statistically significant in bold. Everything else was. So definitely a lot of stops to be eliminated by using the displaced DDI. Of course, here are the vehicle conflict points of the displaced DDI. It has a total of 20 conflict points. Here, 6 diverging, 6 merging, and 8 crossing. This is just a preliminary safety analysis. Of course, the main purpose of this study wasn't to do safety, but it's a preliminary and quick safety analysis, so I chose to include that. And compared to the other 3 interchange designs, it should be no more dangerous than both the diamond and SPUI in terms of the number of total conflict points. The DDI should be safer because it has 14 as opposed to 20, but still, the displaced DDI shouldn't be less safe than the diamond and SPUI based on this preliminary analysis. And so, in conclusion, the displaced DDI shows a lot of potential for substantially improving the operational performance of congested diamond and service interchanges. The operational performance is probably the key benefit of using this design. It also shows promise for being no less safe and no more dangerous than both the CDI and the SPUI based on the preliminary conflict point analysis. Now, the primary, I would say the limitation, of course, would be the construction costs of the bridge structures. As you can see from my previous slide, you would have to build around 4 new lanes of bridge structure, which might be expensive. But however, since it has asymmetric geometry, you could decide which side of the existing bridge structure to build the new bridge structure on, which should make the construction and geometric design more flexible. So overall, it's best suited for freeway to arterial service interchanges with very high through volumes and low to moderate turning volumes, with either balanced or unbalanced overall traffic volumes. So of course, future research could focus on the safety and pedestrian performance, as well as cost and constructability, since I only considered the operational performance of the displaced CDI under heavy traffic volume conditions in this study, as well as how it would perform under undersaturated traffic volumes and with connected and autonomous vehicles, which is becoming very popular these days. And also the traffic control devices that would be needed to ensure motorist understanding and safe operation. And with that, thank you.